Hello. Okay, before we get started with our next section, section 7.4, I want to review a little bit on section 7.3. In 7.3, we talked about, in generality, sets. It's a collection of elements that can be data. Statistics, it's data. Or listing of a group of finite values. Okay, now what are we talking about when we talk about finite values? Well, if we looked at a die, one of the dice up here, we know we have a 1 on the one side, we have a 2, we have a 3, we have a 4, and we have the 5. Would write this set as 1, 2, 3, 4, and 5. So this is the set of everything that's on a 6-sided die. And that's what we're talking about in a set, a collection. Well, then we talked about the cardinal number. The cardinal number is the total count of elements in the set. And we do that by saying a lowercase on the name of the set. It tells us we want the number. So if I wanted the cardinal number for a 6-sided die, we would have the number 6. All right. Well, then we can see that the cardinal number can be utilized in collections of these elements. Okay. We also learned about probability. And this was the big one. It's the capital P of some event is equal to the cardinality of the desired event over the cardinality of the sample space. So here we know event, the E, implies the quantity of the event in a given set. And then the S is the sample space. And that is the S. And it implies a listing of all elements in the study. And it has to be finite in order to do probability. So what is happening here? All right. Well, there's some other symbols that we're going to get familiar with, and that is a Venn diagram. It's a picture of relationships. Of two or more sets. So I'm going to cover those in just a few minutes here. I'm just going to do it, and that way we have it done again and make sure you understand. So if I have a Venn diagram, I have a U, I have set A and set B, and we label. All right. In this set, we're said to be disjoint. And this means no elements in a set A, I should say, let's be proper, exist in set B. They don't share anything. Then we have this guy. And we notice here there is an area of similarity. And in this case, we have an overlapping. Some, not all, some elements in set A exist in set B. So they're shared values. All right. Then we have this one. These are equal sets. That means all elements set A are all elements set B. Okay, that means it's identical. They're equal sets. So these are the three items. Well, we're also going to find out that this is called mutually exclusive. Nothing is shared. This is not mutually exclusive. It is overlapping. And these are, of course, equal set. But when we ask for mutually exclusive, that means they share no items. All right, so now we're getting into today's lesson. So we'll get started here on today's lesson. And we're going to start with the union rule. And before I get to it, let's talk about our symbol representation. It's an upside down U. And what it means is that we combine all elements in set A with all elements in set B without repetition. Repetition is because if they share some same elements in each set, you don't want the repetition of those items. If there is an overlapping, that means that we would have the two sets, E and F, and then we'd have to subtract the one set of shared elements. Otherwise, it would be the probability of event E over the plus the probability of event F. Okay, or means to add. So here we go. Now we're going to structure everything around this particular item. So here we have, for example, decide whether the event is mutually exclusive. No shared elements. So let's read it. Winning a baseball game, an action. Saying best a baseball game, an action, unique. Well, you can't do both, right? So they are mutually exclusive. All righty. Now we're going to talk about building a sample space. All right, so we're going to look at a pair of dice, dice meaning plural, die meaning singular, rolled. What is the probability of getting a sum of 10? All right. Well, we know we can roll one die and get a 1, and the other die and get a 1. That's 2, right? Or we can throw the dice and get a 1 and a 2, because they have 6 sides, right? A 1 and a 3, a 1 and a 4, a 1 and a 5, and a 1 and a 6. All right. So that is all the ways we could roll 2 dice starting with 1. All right. Then we could roll again and we could get a 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, a 2 and a 5, and a 2 and a 6. All right, now we're in the 3s starting off. These are listings of all of the sample space. 3 and a 1, or a 3 and a 2, a 3 and a 3, a 3 and a 4, a 3 and a 5, and a 3 and a 6. Again, order is important in this guy, so that we can get a uniformity construction of a table of 2 pair of dice. So now we're at the 4 starter. And when you build a table, you can see the connectivity of totals and structure, and understand why we get a cardinal number of 36. Now I'm at the last one, the 6s. 6 and 1, 6 and 2, 6 and 3, and so on. So we have 36 ways to roll 2 dice. All right, here we go. So they want, now let's look at what they asked for. They want the probability, that's a capital P, and what's our event? A pair of dice with a sum of 10. All right. So let's look at where our 10 is. So let's see. We can have a 6 and a 4, that's 10. A 5 and a 5, that's 10. And a 4 and a 6. All right. So my event, the cardinality of my event, over the int of my sample space is going to be 1, 2, 3 over 36, which comes out to be 1 over 12. All right. And again, if they're small, you're going to be looking at a fraction of what we need. All right. So let's look at our next example. Again, this is our sample space. And this is our cardinality of our event is in pink. And then we got the probability. Now, on this guy here, we're talking about cards in an ordinary deck of 52. All right. Cardinality of cards is 52. And this is the same as our sample space. One card is drawn. Find the probability, and your typo and your instructor, of drawing the following cards: a 5 or a 2. All right. So let's look at our card scenario here. We have ace. Let me do that. Send a black. Spades. Clubs. Of hearts. And diamonds. All right. These are the things we have. In our spades, we have an ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have a jack, queen, and king. All right. In clubs, we have the same thing. I could have had a picture, but this is hopefully better for you. On the reds, we'd have an ace, a 1, the same thing. Diamonds, I'd have right. So now we're analyzing what we have. These right here are called face cards, and we have 12 of them. All right. These are just numbers, and there's 10 of each, 4 of each, and 10 total. There are 13 suits. The suits are clubs, spades, hearts, and diamonds. And this makes up our 52. All right. So then we have 26 black cards and 26 red cards, which makes 52 as well. So we want the probability of either a 5 or a 4. Okay, 5 or a 4. Right. So we're going to write our probability down. Oops, a 5 or 2. Sorry about that. 5 or 2. Well, we still have 4 of them. Sorry. So we have 4 out of 52, and it's an or, so we're going to add 4 out of 52 chances of pulling a 2 or a 5. And that makes it an 8 over 52. All right, so we're going to divide that by 4, and that's going to give me a 2 over 13. So the probability of a 5 or 2, this is a union problem, or the union rule, all right, is 2 out of 13 chance to get it selected. All right, so now we want a red card or a 6. So if I drew a Venn diagram, I would have red, and I would have 6, because those are the two. And we notice that it's overlapping. Because we know there are 26 of the reds, we know that 2 of them, oops, sorry about that, 2 of them are 6s. So we're going to put on here a red 6 and a red 6, and then we're going to have black 6s right here. All right. So we want, this is that union rule. Overlapping. So what we want is the probability of a red card or a 6. All right. So this one's going to be a probability of a red card probability of a 6 minus the probability of a red intersects 6. All right. So we're going to put them underneath. Red cards are 26 out of the 52. 6s are 4 out of the 52. I have 2 reds that are shared. You can see them there. So we're going to subtract 2 out of the 52. And I'm going to have 28 over the 52. I'm going to divide by 4. And I'm going to get 7 times 4 is 28. 4 divides 52. What is that? 13 times. 7 out of 13 opportunity to get a red card or a 6. There you go. Are not exclusive. They share the red 6s. All right, so here we go. Now we want a 10 or a red 6. Now these are mutually exclusive. Right. Probability of a 10 or a red 6. All right. Well, we know that the probability of a 10 plus the probability of a red 6 is mutually exclusive. So we only have those two to contend with. A 10 is 4 out of that 52. Reds are 2, the heart and the diamond 6. So that's 2 out of the 52. 6 out of the 52. Now, we can divide by 2, and I'm going to get 3 out of, and I'm dividing by 2 only, 26. So we have 3 out of 26 times that we do it to get possibly one or the other. All right. So now we want a heart or a black card. These are mutually exclusive. Right. In other words, I've got hearts, 13 of these, and then I have black cards. It's 26 of these, according to my chart. So I want to say the probability of a heart or black card. Probability of the heart plus, because it's an or, probability of a black card. Right. So hearts are 13 because it's an entire suit out of the 52. Or means to add, and black cards are 26 out of the 52. So this gives me 9 out of the 52. All right, so that gives me 3/4. It's very likely we would get that in a probability of drawing either a 13. Now here we have one that's overlapping. And the reason this is not mutually exclusive is because it's got face cards and a heart. A heart, there is 3 that are a heart. And there is a jack of hearts. Ooh, that's kind of thick. I noticed that earlier. Let me look at that a little bit. We have a jack of hearts, a queen of hearts, and a king of hearts. All right, because they wanted hearts. So let's write this guy up. The probability of a face card or a heart. And we know what we have right here is in the face cards. So if I drew the Venn, I would have what? Oh, that's right, overlapping. And this is a heart. So in this case, we have a jack, queen, and king in here. Leaves us 10 red. And in the face cards, I'm going to have 12 minus 3 is 9. 9 and 3 face cards will make 12 face cards, all the face cards. And 13 minus 3 makes 10. So let's write our probability out. So we're going to have this guy right here, the probability of a face card, probability of hearts, minus the probability of cards intersects hearts. We don't want to add them twice. We only want that 3 to come out one time rather than 6 total if I count it twice. So I'm going to have the P of face cards plus the P of hearts minus P intersect, the probability of face cards intersect hearts. All right. So we said this was 12 face cards. And in hearts, there are 13 in suit. And we share the 3 face cards. 22 seconds. That doesn't look like 22, does it? That'll give us 11 over 26. Over 26. Probability is almost half. All right. So now we have the complement rule. Now this one makes finding probability easy because you can rule out the larger condition from the total condition. So here we go. It says the probability of an event can be 1 minus the probability of not the event. Hyphen means not the event. It is everything else in the band or in the set of numbers or data that are not in the set of E. Right. So here we have probabilities with a Venn diagram. Use a Venn diagram to let P of Z 46 hundredths, P of Y equal 29 hundredths, and P union Y equals 58 hundredths. So let me draw one. No, they overlap because the union of all the sets in Z and Y is 58. Right. So we have this guy and this guy. Okay, and this is Z and this is Y. So let's add each of the sets. So the probability of Z equals 0.46. And the probability of Y equals 29. So I'm going to add them. It's like 75 if I did the math right. So, but we're only going to have 58 at the reunion. So P of Y is a minus point 58. All right. Plus what's in the middle. So this is going to be a 17. So point 17 is in the middle. Now we're going to do the math for each of the parts. Here we go. So 46 minus the 117. There are 29 in set Z that are not in set Y. But together, those two make 46. Now we're going to take the 29 minus the 17 hundredths. It's 12 hundredths. There are 12% or 12 hundredths that are only in Y and not shared with Z. All right. So now we have our van. And we're going to add up all these numbers, and they should equal 58. So let's do that. And the reason I say do that is because we have calculators. It's not going to take us that long to verify our findings. 0.29 plus 0.17 plus 0.12. And there it is, 58. So all three of the parts of those circles add up to 58 hundredths. So we have drawn the Venn diagram correctly. All right, so if I have 1 minus the 58, I'm going to get 42 hundredths. And that's what's not in the one or the other circles. It's floating outside because it has to equal 100%. All right, so now we want the condition of not. Probability of not Z intersects, that means shares with, not Y. All right, so let's look at what we have. Not Z. All right, so not Z is everything outside of the circle. Okay, so we got that. Now we're going to do not Y. And not Y is going to be guy. This guy. This is all not Y. Right, now, everywhere the orange is and where the pink is, right, intersects is where the colors change. All right, so what we have here is 42. 42 hundredths. All right. Now, I'm going to stop right there, and I'll do the rest of this lesson in the next go-round, starting with B. Thank you so much for listening.